Okay, oh, let's make a start. So this one will be on how to sketch tan, and once we go through how to sketch the tan graphs, then we'll move on to some of the symmetries of the unit circle. So different things you can do to reflect your circular function values around the unit circle. So general form of tan looks like the general form of pretty much any other type of circular function, or even any other function for that matter. It's going to have a horizontal and vertical translation term, and it's going to have some dilation factors a and n. It's also going to have the possibility of reflections in there as well. Without any transformations, the graph of tan is going to look like this. The way I think about it is basically repeating the overall shape of a series of cubics a bunch of times. That's not strictly true necessarily. These aren't cubic shapes, even though they kind of look like it. And the reason why is because that isn't a stationary point. It doesn't become perfectly flat at that spot. So it's more so just to remember, hey, what's the overall shape like, rather than it actually being a series of cubics. So looks a lot different to the other circular functions, and the reason why is because tan is sine divided by cos. And whenever you do division of functions, you always run into the possibility of a divide by zero error. Any divide by zero errors will always make themselves apparent on a graph as asymptotes. That's why you have these vertical dotted lines that are equally spaced. Specifically, that's why you have them at plus minus pi over 2 and plus minus 3 pi over 2. Because if tan is sine divided by cos, and cos goes to 0, cos goes to 0 at plus minus pi over 2 and plus minus 3 pi over 2. And so for that reason, you're going to have those vertical asymptotes at those spots. Because cos will go to 0 twice within a period, it'll be at the pi over 2 and 3 pi over 2. Because that happens twice within a period, the pattern of repeat, or the period of tan, is actually pi n rather than 2 pi n. So it's half that of the period of any other circular function, sine or cos. That's a bit on why that is the case. Pretty much most of the times you do this, you'll either calculate it with pi n, or you can even just look and see, look, the distance between those asymptotes, it's pi over 2 one side minus pi over 2 the other. It's going to have a total distance of pi if you add those two up together. Dilation factors work as they always have. They're not really all that relevant to know when it comes to sketching by hand, unless you, for whatever reason, have to sketch both on the same axes, which has never happened. But if for whatever godforsaken reason you do get that, then this is what that would look like, where a larger value means it's sort of a bit more, it's a smoother rise and it's a smoother wobble versus a much smaller value. It's much flatter in the middle. N, just like other circular functions, will change the period of the circular function. So if you have tan 2x, instead of having pi over 2 and minus pi over 2 here, you've now got half of that. So yeah, that's really all that's going on there. And again, if you think about like the whole sine divided by cos situation, that's because you now have cos 2x equals 0. 2x equals pi over 2, x equals pi over 4. So it's the same sort of logic that applies here as well. I said that wrong the first time, didn't I? I said pi n rather than pi over n. This is what I meant, pi over n, rather than 2 pi over n. And again, there's the reason why it goes to 0 twice within a cycle. Yeah, so some key takeaways. Dilation factors don't really matter a whole lot when it comes to actually sketching it by hand. And the n value can be used for calculating the period, but if you're following the procedure that I outline here, you won't actually be using n for any of the actual key features of sketching. Yeah, that's about it. So, example. This one's just got the dilation factors involved, and we want to sketch it from negative pi to pi. First up, My preferred way of finding the asymptotes for tan, just in general, is to do the whole sine divided by cos situation. So if you have tan 2x, then that would be the same thing as having sine 2x over cos 2x. So if you want to find where your asymptotes are, you find where this, the cos 2x, is equal to 0, and you do that over the full domain. There is a specific calculation you can do. It's that. So if you want to do that instead, by all means, go ahead and memorize that if you like. My preference has always been to do it this way because at least this is stuff you already know how to do. You know how to solve cos equals 0, whereas this is just another thing to memorize. But again, up to you. The other disadvantage with this, I believe, is that this only works when there's no translation. Yeah, when there's no translation terms. I think there's another, yeah, it changes. So as soon as you have dilations, it updates. And as soon as you have translations, maybe not translations. Point being is that it changes for different circumstances, and that just seems like a lot of work to me. Whereas you can just be like, hey, cos equals 0, and that's the whole thing. So that's what we do here. So if you want to solve where cos equals 0, well, that's going to be a plus minus pi over 2 and plus minus 3 pi over 2. I've done my whole little substitution method to fix up the domain. And then, yeah, all you do is you divide through by 2 at the end. That gives you your two things. It's very repeatable because cos will always go to 0 at pi over 2 and 3 pi over 2, the plus minuses of those. So you pretty much arrive at the same answers every single time you do this. It's very repeatable. So that gives us our asymptotes. Next up, we need x-intercepts. So a couple of ways you can do this. Every single time it works by finding where function equals 0. That's how you solve any x-intercept, let y equals 0. However, when there's no translation terms that are going on, you'll find that the x-intercept will always appear in the middle of all of our asymptotes. So the middle of each of these sets of asymptotes is also where you'll find your x-intercept, so long as there's no vertical translation. Even horizontal translations work fine with this. And so instead of doing where tan equals 0, you could instead just do, okay, I got pi over 4 and 3 pi over 4 here. The midpoints there are going to be the pi over 2's, and so on and so forth. But if you did want to do it the other way around, then instead of calculating midpoints, it would look something like this. From there, if you have endpoints, which oftentimes you'll do, this will expand out to all real numbers, so you should find the midpoints, the endpoints rather. Although in this specific case, it turned out that our x-intercepts are endpoints. So you have plus minus pi as x-intercepts, and we're trying to sketch from negative pi to pi. So that one just kind of worked out for us in our favor. If you didn't end up with those exact, then you would have to sub in pi and negative pi into your function, and that will give you the y values at those spots. And then from there, you just kind of want to get the overall shape working. We had positive tan, so it's going to start bottom left and top right. Whereas if you had negative tan, it'd be top left down to bottom right. It works the exact same way as the cubic works. Yeah. Anything to clarify further there? I've already talked about these reflections. Yeah, works the exact same way as a cubic does. So, translations. Horizontal translations, shift everything right or left. So, in this case here, you got to shift right by pi over 2. So instead of having asymptotes at plus minus pi over 2 like it normally would, they're now going to occur at 0 and pi. Horizontal translations tend to make the graph look nastier than it otherwise would have. You can see we've got asymptotes on an axis this time, and it's a bit, I don't know, feels a bit weirder looking at it this way. But overall, it's the same sort of idea. The good news is you don't really have to even consider the fact that there's a horizontal translation in your graph, because if you're following the procedure I outlined earlier, it kind of just gets baked into where you find your asymptotes by doing cos equals 0. so it doesn't really become an actual consideration when you're doing it by hand. Here's another example, shifted left by pi over 3 instead. Where it gets a bit more painful is when you have to do vertical translations. So one of the things to consider about vertical translations is that it sets the y value of your inflection point. So this is a shift up by 1, it's tan x plus 1. And so our inflection point is going to occur at y equals 1. Now, the x-coordinate of that is still going to be at the middle of your asymptotes, as always. So asymptotes, middle. But now that it's been shifted up by 1, you now get an inflection point there. That's not a key feature you have to actually outline. This is more so just me showing you that that's what that looks like. Now, the real painful part of this is noticing the x-intercepts here. They kind of all just shoot off a little bit offset from that middle. We don't have the advantage of doing that midpoint thing anymore. And so to get these x-intercepts, when there's a vertical translation, you now have to do y equals 0 to solve that. And what I've noticed in the book, at least I think I've noticed in the book, is that some of those just can't be solved. Like tan x plus 2, if you rearrange that, there's no spot on the unit circle where tan equals -2. This is a thing where you have to do it by cas for whatever reason they've done that. So just keep that in mind when you start doing those questions on your own. You might have to use cas for some of them. Yeah, and so the overall procedure of sketching any tan can be basically boiled down into these seven steps. Get the function into a spot where you can see everything you need to see. Solve the cosine to get the asymptotes. Vertical translation will give you where that inflection point is. Figure out the shape. Is it bottom left, top right, or top left, bottom right? Axes, intercepts, endpoints, so on and so forth. So here's a nasty one that has a little bit of everything. We're just going to do, you don't even really have to do much rearranging here. I just like doing it because it'll tell you what all those transformation factors are, but you don't necessarily need it to sketch. It just kind of helps by understanding what you expect to have happen. So we get our full tan there. If you want to find asymptotes, you basically just replace the word tan with the word cos, and then you just solve for where that equals 0. So you want to solve that equals 0. Again, it's going to be your plus minus pi over 2. Yeah, this is just solving circular functions like we've done plenty before. So if you want me to explain that in any more detail, just like a thumbs up or whatever, and I'll do so. But otherwise, yeah, you're going to be your plus minus pi over 2, plus minus 3 pi over 2, and then you just rearrange that x value as accordingly. This one's obviously nasty because the fractions are a little bit offset from each other, so you're going to get some nastier values, but fundamentally it's the same thing. Where's cos equals 0? That gives us our asymptotes. Then from there, vertical translation. So you can see there's a plus 2 there. So our inflection point is going to occur at y equals 2. It's not really a key feature. That's more so just so you can get the overall shape looking at least somewhat passable. Identify the shape. So really it's the reflection terms that you want to spot here. It's negative tan, so instead of being top left, instead of going bottom left, top right, it's now going to be top left to bottom right. Works the same way as cubics. Because we have a vertical translation, we do have to solve the axis intercepts individually. So y-intercept let x equal 0, nothing too crazy there. X-intercept let y equal 0. This obviously can only really work under like 3 conditions. Do we have tan equals 1? Root 3 over 3, or root 3. That and the negative versions of those, of course. And so yeah, you just want to solve where tan equals that. So again, just where does tan equal 1? Give you those values. Remember, over that specific domain, rearrange. Nothing too crazy. Maybe a little crazy as far as the values themselves, but the actual steps that you're following, it's still just solve circular function. And endpoints if we need them. So in this case, again, endpoints were found in the asymptotes section. So we wanted to sketch from minus pi over 2 to pi over 2, and as it turns out, those were asymptotes. So we kind of already have those endpoints there. So we got those. Now we just plot. So we had our asymptotes, we had our inflection point, we had our intercepts, and then yeah, you just plot that all out. I like to draw out the asymptotes as soon as I get them. That gives me a little grid to work with. Then from there, what I'll do is I'll draw the actual shape first, and then wherever that shape cuts, I then put my interval tick on that. That way, I don't force myself to draw a wonky looking graph. I draw a slightly less wonky looking graph and then put the interval where it ends up. That's really it there. Anything to clarify further? Okay. So what I'll do is I'll get a screenshot of the summary. That gives you the procedure to follow. And again, you don't have to do the asymptotes the way I do it. If you like those equations, then you can use those. But yeah, so I'll even get a screenshot of those should you be at all curious of those. Where is it? Here we go. You kind of need the context of the whole thing though. So this works for A and T. Yeah, okay. So if you've already been taught those, then feel free to use those. Okay, so first up we'll do one of the question 2 ones. That's just with the A and N only. So let me write one of those down. Y equals tan 2x. All right, so if we're going to sketch that following, well, what do we think the first step's going to be for sketching this? Yeah, finding asymptotes. That's good. So how do we find the asymptotes in this case? Cos 2x equals 0. Yeah, correct. Absolutely. You just replace the word tan with the word cos. Probably should have figured out our domain. We're doing negative pi to pi. Okay. So we have x element minus pi to pi. And so yeah, we replace the word tan with the word cos. Cos 2x equals 0, and we're solving it over that particular domain. So we can fix this domain up if you like. If so, let me know what that would look like. Otherwise, we can just dive straight into solving it if you're confident going straight into that. What should we do? Make the domain, times the domain by 2? Yes, correct. So it's basically u equals 2x, and therefore we've now got cos of u equals 0, and you sub in both of those x values into the u, therefore giving you a u domain of minus 2 pi to 2 pi. Yeah, exactly. That's how you fix that one up. Nice. And then yeah, solving cos equals 0, where what are the solutions of u in that domain for cos equals 0? Not 1, this will be like the pi values. So it's just what does u have to be for cos equals 0? So like on the unit circle, like what are these cos equals 0 here and here? What are those two spots? Yep, pi on 2 is one of them. And 3 pi on 2. Yeah, correct. It's both of those. So you got pi on 2, you got 3 pi on 2. That gives us from 0 to 2 pi. That's pretty good. How do we get the other? Because you've got to go all the way to negative 2 pi as well. What's going on there? Not sure. Okay, so basically the way you handle split domains is you basically start at 0 and then go forward, which is what you just did. You went 0 to 2 pi and you got those two solutions. Now you just do the opposite. You go from 0 and then backwards. So if you think about how you go backwards around a unit circle, it just means instead of going this direction, you go in the opposite direction. But you make all the values negative on this way around. So in that way, this becomes negative pi over 2, and this becomes negative 3 pi on 2. So it's just go in the opposite direction and then make the values negative as you hit them. So the succinct way of saying that would be plus minus on both of those. Fair enough on how that works? Yep, sweet. Okay, so that gives us, like this is the same thing every single time, because if you're doing this sort of rearranging the domain thing, you'll always get u equals plus minus pi over 2, plus minus 3 pi over 2. And if it was a bigger domain, you'd continue plus minus 5, plus minus 7, plus minus 9, pi over 2s, all of those, until you fill out everything you need. Yeah, that gives you that. So where do we go from here now that we have u solutions? What, the asymptotes? Kind of. So we have u solutions, but our asymptotes need to be in terms of x. So how can we get them in terms of x before we plot it out? Divide by 2, correct. Yeah, and the reason why is because u equals 2x. So we have 2x equals all of these solutions. And so to get x on its own, we just divide everything by 2 in there. Yeah. So we now get x equals plus minus pi on 4 and plus minus 3 pi on 4. And so when you get this final answer, you can now look back at the original domain negative pi to pi and realize, yep, I got everything that fits within that. There's no ambiguity if there's any more to find. Yeah, and now that we have that, we can now plot out those asymptotes on a graph. Have our minus pi, pi. Those are going to be like endpoints, and then there we go. Pi on 4, 3 pi on 4. Bit squashed, but better than most. Most of my graphs, anyway. Sweet. All right, asymptotes acquired. What else do we need? x-intercepts? Yeah, a couple ways you can do that. How do we get x-intercepts? Y equals 0, yep, that's one way of doing it. And the other way would be midpoints. So I'll just do the midpoint thing first, and then we can do the y equals 0 approach. So between plus minus pi over 4 is going to be 0. For this one, that's pi over 2, but as far as how you calculate that, you would do pi plus 3 pi over 4, and then divide that result by 2. So 4 pi over 4, so pi, and then divide that by 2, gets you to pi over 2. That gives you that, and that gives you minus pi over 2, since it's symmetrical. The y equals 0 approach just means we have 0 equals tan 2x, and you just need to figure out where tan equals 0. So on the unit circle, where does tan become 0? Zero is one of them, yep. That was that one. There's another spot where tan goes to 0. Pi. Yep, that's the other spot on the unit circle, which is good. That's pi. And remind that our domain is from negative pi to pi, so there's one more to hit. We've hit both spots on the unit circle, obviously, but now we need a negative solution. Negative pi, correct. Because instead of going in the positive direction this way, you go in the negative direction that way. So plus minus pi, and then obviously to get the x on its own, 0, and then plus minus pi on 2, which sure enough we got from earlier. So this one's personal preference. If you're really, really quick at your circular function stuff, you'll be able to get this quick and then plug them out, versus doing midpoints, which only really works if there's no vertical translation anyway. So if you're going to pick one to be a master of, then probably this one will be the way to go, because that works always. Yeah, that's everything there. Now we just got to sketch, because we got our well, we haven't really labeled the endpoints just yet, but probably no. Actually, it is probably better off to get the endpoints before we draw the lines. That way, we don't have to redraw the lines if the endpoints look a bit weird. So, did we actually have any values for that? Nah, we didn't actually get any of the pi or negative pi in there. So how could we get the endpoints at plus or minus pi? Sub in negative, yeah, sub in negative pi and pi. Correct. Whenever you have endpoints for any graph, you just take, yep, that's my x value, so I've got to plug it in. Yep, that's my x value, got to plug it in. So yeah, you would do, the first one would be y equals tan 2 times pi, because it's x equals pi. And tan 2 pi, well, based on what we were discussing earlier, 0 pi, 2 pi, 3 pi, all those are going to be 0. So that's definitely a 0. And the good thing about tan is if you stick a negative on there, it's the same thing. It's also going to be 0. So both positive and negative pi, when you sub those in, are going to be zeros. So we know it cuts there and it cuts there as an endpoint. So the last decision to make is the overall shape. So they all look like cubic-like shapes. Are we doing top left to bottom? Yeah, top left to bottom right or bottom left to top right? I said top left. So the first one I said, I believe, was this. Is that what you meant? Maybe I just forgot the order I said them in. Basically, is this right? Other way, okay. Yeah, correct. Yeah, the other way around. So positive tan, positive cubic. That's one way I think about it. Let's make this green. Might be a bit easier to see. Mean, bang, hit, hit, and this one you gotta go backwards on. And that gives you the overall shape. That would be, now did we do everything? Yeah. This one had y intercept in the correct spot. Yeah, that's sorted. So only thing we didn't have was a vertical translation, but as you'll see, that doesn't actually really change your behavior at all. Like if we had a +1 here, for example, the only thing that would change is when you do your x-intercepts. You put a +1 here, and that means tan equals -1 instead of tan equals 0 in the end. So the exact same process, but that's all that ends up changing there. And same thing for horizontal, right? Like if we had 2x minus pi on 2, we're now just doing cos 2x minus pi on 2. And so it's quite, the translation factors are kind of already just baked into the process, which is why I like this way of doing it. Cool. Okay, so that is that. Does anyone want to see another one of those be done, or would we want to work on the next topic, symmetries of the unit circle? Next topic? Sure. Okay, so this will cover a lot of individual things, but there's an overarching theory that you apply to all of them, or at least the vast majority of them. And the whole idea is that you start with this so-called reference angle. So you'll know when to use this by the information provided to you in the question. You'll see a specific value for sine, cos, or tan, and you'll be told to evaluate a related sine, cos, or tan. And the thing that will be different will be whatever's in the brackets of the circular function. So in this case, instead of just being sine theta, you now have sine 2 pi plus theta. So pretty much every time you get this, it'll just be sine something, cos something, tan something equals whatever. There won't be anything super crazy in the brackets. For that reason, that allows you to create what I call a reference angle, which just means you chuck whatever the information is into a unit circle diagram. So sine being equal to 0.43 just means that whatever that theta angle is, the y value for which the line intersects is going to be at 0.43. We don't have any other information. We don't have any x information there. We don't even technically know that it's quadrant 1. This could be quadrant 2 because it is sine, positive in both of these. But what you'll find is that every time this question's written, it'll have a positive value here. And so you can always just default to top right, and then that streamlines the whole process. So first up, the first symmetry property we look at is periodicity. We already know this one. It's the fact that a circular function, sine or cos, will repeat within 2 pi. So if I do 2 pi plus theta, that just means I start at 2 pi, which is here, and then add theta, which is here. So I get back to where I started. That's all it is. Start at 2 pi, add theta. Start at 4 pi, add theta. Start at 6 pi, add theta. Same thing. So any 2k pi, or 2 pi n, whatever, plus theta just means start at whatever this thing says and then add theta. In the case of sine and cos, that's always going to get you into the exact same spot. That's also true for tan, but tan is periodic in more than just 2 pi. It's periodic in pi as well. So if you do the tan version of that, it's a bit harder to draw what that looks like there. You can kind of do it if you think about tan being sine divided by cos. You could say it's 29 over 100, and therefore sine is 29 and cos is 100. It's sort of whatever. So I usually just leave an xy there, and I'll make sure to highlight, hey, that means tan is 0.29, tan is positive up here. So pi plus theta, similar to what we were talking about before, whatever's here is where you start. So in this case, because it's pi, it means we start here. And because it was plus theta, we add theta. So whatever that looks like, you just go from quadrant 1 to quadrant 3. And when you do that, both your x and y are going to flip to being negative. Now, that would mean sine and cos change, but because they change in the same way, tan actually remains constant. Negative divided by negative, still a positive. That's periodic functions, but depicted on a diagram. Anything to clarify there? All right, next up. These are called the half-period formulas. There are a lot of them, so you can either memorize what these look like in equations, or you can use that whole reference angle approach. So let's look at them. Again, very similar setup. Here's sine theta, now do sine pi plus theta. We kind of already looked at what pi plus theta is all about. You start with your reference angle. In this case, since you know sine, you know the y value is going to be 0.72. When you do pi plus theta, you start at pi, you add theta. That makes both sine and cos negative, which is why we go from being 0.72 to now negative 0.72. You can see that they flip. In the opposite direction, if you have pi minus theta, that means start at pi and then go backwards by theta. When you go backwards by theta, the only thing that changes is the x value. So when you compare the two y values, you realize, okay, sine is still just 0.72, whatever it started as. When it comes to cosine, again, cosine plus pi plus theta for cosine, because they're both negative here, that makes sense. They should be, the cos should still be negative. Whereas when you do pi minus theta, sine was positive, but cos is still negative in this second quadrant section. So our 0.84 is now flipping to negative 0.84. Tan, we already did this. So we did the pi plus theta for tan. We didn't quite do the pi minus theta though. Pi minus theta just means, okay, we're in this quadrant too, but because there's now a mismatch of signs there, instead of it being a positive tan value, it's now a negative tan value, because tan's negative in this quadrant. Or the other way to think about that is sine divided by cos. Sine is positive, cos is negative. Tan must therefore be negative. Anything to clarify with those? And if I'm moving too fast and you don't have time to type something in, just type it anyway and I'll stop. Okay, reflection properties. So again, 3 more things to look at. Either memorize those, or we can use this sort of reference angle approach. So we have a value of sine. What is sine of negative theta? Well, negative theta, as you might, there's a couple ways you could memorize that. Negative theta either means just reflect downwards, or you can think of it as just going backwards in the same direction around the unit. Oh, sorry, backwards in the same amount from the unit circle. So it's either from here up or from here down. Point being, you go from quadrant 1 to quadrant 4, and for that reason, sine is going to be negative, cos is going to be positive. So that sine value that was 0.37 is now negative 0.37. that cos value that was 0.19 is going to stay 0.19 because again, you're in the spot where x is positive. For tan, you're going from quadrant 1 to quadrant 4, and so once again, your positive is now going to become a negative. So a lot of these earlier ones are pretty much just where is sine, cos, and tan positive or negative, and then that informs your decisions. Next up, quarter period formulas. There's a whole bunch of them. Again, it's not, you don't have to memorize all this. You just have to know this overall technique. Okay, so this is when you have pi over 2 plus or minus theta. The way this works is the same way it's worked before, which is whatever the value is, you start at that spot on the unit circle. If it's plus theta, you go to the left. If it's minus theta, you go to the right. In this case, we're looking at pi over 2 minus theta, which is going to end us up back in quadrant 1, but with a bit of a twist. The x and the y values swap positions. We have actually seen this before. This exists on the unit circle right now. If you do, if your angle is pi over 6, and you do pi over 2 minus pi over 6, you get to the pi over 3 spot. And if you compare those two coordinates, you realize that they're just a flip of each other. And the reason why is because, well, if you're starting at max y value and moving down, it's a very similar thing as starting at the maximum x value and then moving down. It's just the values themselves are going to change x, y dependent. So we have seen evidence of this in the unit circle before. This is just my way of saying this isn't hell to remember. So if you ever see pi over 2 type stuff, you can even just like imagine your unit circle in your head and know, the values swap. So that's pi over 2 minus theta. As far as plus theta, it means we're going to end up in quadrant 2. So the thing there is, no longer do they just swap around, so xy becomes yx, but they also, because they're now in quadrant 2, whatever's in that x spot is now becoming negative. Now I say the x spot rather than the x value because, well, these things get moved over a whole bunch. It's just whatever's the new x coordinate, which happens to be that spot, becomes negative. And again, we can see that on the unit circle. If you do your pi over 6 angle, then pi over 2 minus pi over 6 gets you to pi over 3, or pi over 2 plus pi over 6 gets you to 2 pi over 3. If you compare those two things, you'll notice that the same coordinate, with the exception that the x value is now negative. That's all that is. So obviously I've got a bunch of examples for how that works. You can see at the top what the mathematical way of representing that is, but you don't really need to memorize that. You just need to know how to draw it, and then you can go from there. Or memorize it. I mean, I, to this day, have not memorized these. I just draw this. Okay, so we have cos, evaluate sine, pi over 2 minus theta. So we draw out our red reference angle. Cos is 0.72. Pi over 2 minus theta means start at pi over 2, subtract theta. That's going to cause the values here to flip. And so when I want to do sine of this spot, I have it. It's 0.72, since it's the y value. Not this, but the actual y coordinate itself. So for that reason, they flip. Same thing with cos, exact same idea. Flip the coordinates. And then pi over 2 plus theta, again, flip and make negative. So what you'll find is if you start with cos will be 0.86, it'll be chucked to the right-hand side, and then when you go over here, because it's now a y value, it doesn't change anymore. So when you do this whole flip stuff, cos stays as what it was. And then the opposite occurs for sine, right? Sine was 0.43, it got flipped into an x coordinate, and now that it's on this left-hand side, it's going to go negative. Tan is a bit of a weird one, but the same principles apply. So we've got tan is 10 over 7, which gives us some initial xy. Pi over 2 minus theta means it flips. But as far as what that means for tan, it just means you flip the numerator and denominator. So you'll find that these will typically be fractions, otherwise it's a bit difficult to work with. You might get something like 0.1 or 0.2. Just convert that to a fraction first. So 0.1 would be like 1 over 10, and then you flip that to just 10 over 1 if you need to do that flip. So point being is just you flip numerator and denominator because y divided by x, or sine divided by cos, those positions have reversed. Same thing with plus theta, but because you're in quadrant 2, you're now making that value negative. Those are all the flippy stuff that we do, all of those symmetry properties. There's a few more little tips and tricks to, I think that maybe there's only one actually. Yeah, only one left to go. Anything to clarify on this pi over 2 plus minus theta shenanigans? All good? Hell yeah. Okay. Pythag identity. You've seen this before. You have a triangle, hypotenuse squared equals cos squared plus sine squared. And the reason why it's a 1 there is because it's on a unit circle. Right? You've got a hypotenuse of 1, adjacent, opposite, all those values squared equal hypotenuse squared. This is useful when you have a specific circular function and you want to find, the value of a circular function, and you want to find the values of the other circular functions when they don't have different transformations involved in them. So you can see this is sine x, cos x, tan x. It's not like sine x, cos x plus pi over 2, tan x plus whatever. There's no changing values in there like there were for all of these. Like, see how they're all different either side of this equation? If there's no changing values, then what you do is you would use the Pythag identity, which just means, okay, I know what sine is. I'm just going to plug that in the sine spot. Sine squared plus cos squared equals 1. Well, if sine is 3 over 5, then I now have 3 over 5 squared equals plus cos squared equals 1. Rearrange that for cos. You'll always come into a situation where you have a plus minus. That's the nature of square rooting both sides of an equation. That's where this separate part comes into play. You'll be told a domain that's associated with your particular equation. Under those circumstances, that'll help you figure out what your value should be. It'll either be positive or negative in a given quadrant. It can't be both. Right? Like for cos, on the right-hand side is always positive, on the left-hand side is always negative. It'll never be both. In this case, pi over 2 and pi as our boundaries mean we're talking about quadrant 2. And so for that reason, cos is going to be negative because, well, cos is negative in quadrant 2. So you take the negative of that value. Once you have sine and cos, finding tan is just a matter of doing that division. So you do your sine divided by cos. My preferred way of writing that, so I don't stuff it up, is to use an actual division symbol. So I've got my sine, which is 3 over 5, divide my cos, which is negative 4 over 5. And when I do it that way, it's pretty chill to just flip that into a multiplication and then solve, versus if you just write this by hand, like stacked fractions on top of each other, that can be a bit painful to look at. But yeah, that's going to give you your tan value. So all in all, we've had a look at all of those. All of these are covered by a few key rules. You kind of already know this one from sketching. You know this one from solving. These and these, they each have the same sort of idea. It's just whatever's in that left-hand side spot is where you start, and then you either add or subtract theta from there. This one, nothing crazy. This one, you flip. So all this gets boiled down to the same sort of idea. So anything in there left to clarify? Okay. Lots of stuff there. Let me just double check where the actual questions for this are. 14D. Yeah, okay. So what I'll do is I'll get a screen grab of this whole thing if you want to like see the equation versions of these. And then I'll get a picture of, yeah, I guess any of these works. So you can at least remember the overall idea of solving this. Okay. 14D. Yeah, so the way they do it in the book's a bit fun, where they give you here's sine, here's cos, here's tan, but what they've done is they've given you different angles involved. So the way this one ends up working out is that you do 3 separate reference angles. You do one for theta, you do one for x, and you do one for alpha. So let's try to give that a shot. If I wanted to create a reference angle for theta, what's my coordinate going to look like? Oh, sure, you write it down actually. We've got sine, let's put it down here. Sine theta is 0.42. What would my reference angle coordinate look like? 0 and 0.42. Yeah, correct. 0.42. We can do another one for cosine. Let's try and do an actual circle this time. This is our x, and it's cos x equals 0.7. What's that coordinate going to look like? It's 7 comma. Oh yeah, I just realized. Shouldn't necessarily be a 0, should be a y or an x. Yeah, I just caught that now. But otherwise, yeah, that's fine. Because if we knew the value, I mean, it doesn't actually change how you solve the question because you'll never actually use the unknown value. But in the interest of being accurate, yeah, you would leave that as an unknown rather than a 0. But otherwise, yeah, otherwise that's fine. Even if you made that mistake, you'd still get it right. And then a weirder one, tan. So as long as you do something that makes enough sense to set up this coordinate, I'm fine with it. There's a couple of ways you could do it. This one is tan and alpha is 0.38. Alpha 0.38. Yeah, so this one you just leave as an x, y. That's my preferred approach. Or if you like to actually have the information embedded in the unit circle itself, one thing you can do that's technically wrong, but still useful, is you think about this as 38 over 100, right? So 38 over 100. That means your sine is 38 and your cos is 100. So that way it's embedded in the actual unit circle. So when you do flips and whatever shenanigans you have to do with it, you can then go back and do your y divided by your x to get that tan value back. So either of these is fine. If you use the xy, obviously keep this tan thing around. Otherwise, this is all you really need. Cool, so that gets us some unit circles. Now, if we just do some miscellaneous whatevers, if I wanted to do on this circle pi over 2 minus theta, where does that put me? So we'll say, what's sine pi over 2 minus theta. Wait, sorry, what am I saying? Not pi over 2, pi minus theta. Where does that go on this unit circle? Second quadrant? Yeah, that's good. Pi minus theta. And so what actually goes there as a... You can either tell me the full coordinate or you can just give me what the value would be for this answer. Yeah, minus... Well, hang on, it's sine though. Yeah, positive 0.42. There we go. So this coordinate would end up being negative x and then 0.42 because y values don't change, quadrant 2. So, yeah, stays the same. Let's try this one here. We can go cos of pi plus theta this time. So if we're looking at this unit circle here, pi plus theta puts us where? Third quadrant? Yeah. Because you start at pi and you plus theta, which gets you down here. So either coordinate or what's cos plus pi, pi plus theta? Minus 0.7, yeah. That's good. Minus 0.7 because both things become negative down here. And then what else? Here's a trickier one. What if I said tan of... Now, how can I do this properly? No, actually, no, yes, I can, I think. I think I can do this. Tan of 3 pi over 2. We'll do plus theta. I haven't shown you 3 pi over 2 yet, but I'm curious to see if you can figure it out based on what we do. Where does that belong on this unit circle? Fourth quadrant, sure does. Yes, nice. Now, it belongs in a little bit of a weird way. What do we do when we have to have 3 pi over 2 type stuff? What happens then? Yep, that's fine. Any pi over 2 type angle will cause the coordinates to flip positions. So whether that's pi over 2, 3 pi over 2, 5 pi over 2, anything that isn't divisible down to just an integer will cause it to flip positions. So not only do we have to be in quadrant 4, so y becomes negative and x becomes or stays positive, but you also have to flip the positions. So you've now got a 38 here and a 100 here, but because it's y is negative, you make that a negative there. And so when you finally do your tan, when you do your y divided by x, you've now got negative 100 over 38, which just simplifies. So minus 100 on 38, which, whatever, it's a fraction. Someone can simplify that. Yeah, so if there's anything to clarify there, please let me know. Otherwise, this is end of class. Take care.